There are several ways to model a float diaphragm in STAAD. We can use rigid float diaphragm or control dependent relation to consider the in-plane stiffness of the float slab without even modeling it. For more accurate analysis and design, we can model it using finite element mesh. For this 10-story building, I am using the second approach. I want to model the float diaphragm and shear wall using finite element mesh. In last two videos of this series on finite element mesh generation, I have discussed about basic plate modeling techniques. Initially, the slab was modeled with a single plate element for each panel using infill plate option. But that procedure did not produce correct model due to lots of improper beam and plate connectivity problems. Also, the load transfer was not accurate. So, I have decided to go for basic plate mesh using generate mesh or create mesh option. This mesh generation technique is useful for regular panels, but for irregular panels, this is a lengthy process as we need to generate plate mesh for each panel separately, maintaining proper boundary division and connectivity. Not suitable for this structure. There is another option which I think is the best solution to generate any plate mesh. Hi, my name is Surajit Ghosh, and in this video, I will discuss about the advanced mesh generation option available in STAAD, which is known as parametric model, and let you know why it is far better than any other mesh generator. There are several advantages of this advanced measure, which I will discuss in this video. So watch till the end. Parametric model was present in the older V8i version, but it was included in STAAD Advanced license. You can use this mesh generator only if you have STAAD Advanced license, but in Connect Edition, this module is included within STAAD Basic license. So if you are using Connect Edition, then whether you have Basic or Advanced license of STAAD, you can use this Advanced Mesh Generator module. If you are still using V8i version, then you need to check your license configuration before using this. Let's check how to use this module. Whenever we select this option, entire model is disappeared and all existing beam and plate are displayed using a dotted line, which work as a reference to mark the geometry. To generate an advanced plate mesh, we need to define the boundary of the panel, and whatever object is present within this boundary will be automatically considered during mesh generation. Now, if we try to select the boundary of each floor panel from here, it might be incorrect due to overlapping panels. What I suggest, first isolate a floor or any panel which we want to mesh using this option. That clears the window and helps to select the boundary easily. Normally, I save different views for different levels, and I can easily select any level from the view list. For this model, I want to generate a plate mesh at 5th floor level. I can easily isolate this floor panel, including the supporting columns. Once we select the parametric model, all options related to this module are available in the right window. First, we need to add a region which will be used for mesh generation. You can notice the cursor is now changed, and using this, I am going to select the same portion of the slab which I have used in my previous video. Remember, last time it was unsuccessful as the internal members and nodes were not considered in the mesh. You should check part 1 and 2 to get a full idea about various mesh generation techniques. One of the advantages of parametric model is we can select the corner nodes only to define the boundary and ignore any internal node. all the internal members and nodes will be automatically considered in the mesh. I'll show you how. And after selecting all the corner nodes, we can select the first node or click the right mouse button. This will display the mesh generation options. We can specify different name for each mesh. This will be helpful to identify the mesh easily if there are multiple meshes. We can specify the mesh type as wall or slab depending on the structural element. And on basis of this type, subtype options are modified. Like if we select slab, then we can further specify this as slab of a tank. Similarly, for a wall, we can categorize it as wall of a tank. Do you know when this subtype is required? Starting from Connect Edition Update 6, a new structure wizard is included in Physical Modeler to generate a tank model. If you use this module and generate a tank model with FEM, that can be further used for design using Eurocode with RCDC module. If you don't want to use this module, then also you can model a tank in Analytical Modeler and design using RCDC. For that, you have to generate the tank wall and slab using parametric model with proper subtype as wall tank or slab tank. Only if you define the slab and wall of a tank using these subtypes, then RCDC will recognize it as a tank element and design. Else, the tank model will not be designed and only used for analysis. So, this subtype is used only for tank structure. For any other model, set the subtype as undefined. For this slab panel, I am going to select the type as slab and subtype as undefined. Next, we need to specify the meshing method. There are two options. Basic method generates a plate mesh with triangular plate element, whereas standard method generates a quad plate mesh. Boundary connectivity options are very important for mesh generation. Remember the basic plate mesh options? We need to define the edge division along with the bias for each side. Here also we can define the number of segments for each edge of the panel. But there is a better option. Optimize boundary segment. Using this, we can inform the program to divide the boundary in such a way that the entire mesh is optimized and generated plates has proper connection with existing plate and beam. I don't know how many segments are required to consider this column junction. So I can simply select the optimize option and program decides how many segments are required to maintain proper connectivity at this location and generate plates with proper aspect ratio. I always prefer this option. We can also specify the target element size. This input defines how coarse or fine mesh will be generated. A large number means a coarse mesh with larger plate element and vice versa. Note that this is not the length of the generated plates. zero point 0.8 does not mean 0.8 meter square plates will be generated in the entire panel. This is just a limiting value, and during mesh optimization, plates will be generated with maximum edge length less than or equals to this value. For first trial, don't provide a smaller value. We can check and rectify the mesh density later, so I'll start with a larger value. The next input is very important. If we want to consider internal nodes and members during mesh generation, then we need to select this option. As you can see, in this region, there are several internal members and column nodes which I have not selected during boundary declaration. If we select this option, then program identifies all these objects and these are considered during mesh generation. I'll show you how these internal objects are used. Finally, we can add openings in the mesh. For now, I'm going to skip this. Once we click on OK, you can notice a mesh is generated in the model and also these mesh details are mentioned in the right window. But these elements are not yet added in the model. Rather, they are just a preview of the mesh with current input. And we can still modify this or remove this without affecting the model. In basic mesh generator, there is no option available to preview the mesh. But in parametric model, we can provide some initial inputs, generate the preview of the mesh, and we can further customize the mesh from here. Like we can change boundary division from automatic to user defined and specify the division numbers. Change the meshing method from standard to basic. This mesh is generated with rectangular plates, and if we change the method to basic, then triangular plate mesh will be generated. Also, we can modify the target element size to change the mesh density. I prefer to generate a coarse mesh at the beginning and review the mesh density. Then change the target element size to create an optimum mesh. If we click on Apply, see, a new mesh is generated with triangular element, which is very fine. We can further modify it. Isn't it great? Let's review the other information. Though we have selected only the corner nodes, but program internally detects all the members present in the boundary, and you can check the node coordinates of each boundary element from here. During mesh generation, we have informed program to consider any node or member present within this region, and those are considered properly through density point and density line. This is one of the most useful advantage of parametric model, and we can further customize the mesh as per our requirement using these inputs. Any node which is already present within this boundary before meshing is marked as density point. For example, the column head located within this boundary is automatically added as a density point. Similarly, all the existing internal members present within this boundary are added as a density line. During mesh generation, program provides higher priority to these nodes and lines, as you can notice from the generated mesh. Density line defines an imaginary line along which all the plates are created, and for these members, it ensures proper beam to plate connectivity. Compare this with the mesh generated from basic option, and you can clearly notice the difference. For basic mesh, plate edge are not in line with the member, as these internal members are not considered during meshing. So it has a beam plate connectivity problem. These are auto-identified lines. We can also declare a new density line to divide the mesh. Say there is an internal wall at this location, like a partition wall, and we want to apply a line load along this. With current mesh, it is not possible to add a line load as the plate corner nodes are not in a line. To solve this problem, we can add a new density line. We can use the existing grid or customize it to add this line. With this new density line, mesh is now generated in such a way that all plates have a corner node along this line. We can add a line in any direction, and that will govern during mesh generation. Similarly, we can add a new density point using grid or coordinate value, and meshing will be readjusted to include the node in the mesh. These options are very useful to add a line load or point load on the mesh. If we change the mesh density now, then also these lines will be considered. There are two more options. First one is used to add an opening within the mesh. This is similar to the basic mesh. We can add a polygonal or circular opening, but this time we can use a customizable grid to define the boundary of the opening. No need to calculate the corner node coordinates. To add a circular opening, we can select the center node, any node on the periphery, and specify the edge division. With this input, program generates an opening within this region, and all the plate elements will be rearranged near the opening. We can further modify the radius or the edge division if required. We can also add a region. It is similar to an opening, but for a region, only a closed boundary is added to the mesh. This option is very useful when we want to apply a patch load on a slab or mat, like load from an equipment. Also, this can be used to specify different thickness to any portion of the slab, like to model the drop cap portion for a flat slab or punching shear zone for a mat foundation. We can simply define the boundary using grid, and within this region, a mesh will be generated with plate edge along the boundary. This is like a mesh within a mesh, and we can easily select the plates within the region to apply load or assign different thickness. I'll create a separate video on flat slab modeling later. And once we are satisfied with the mesh, we can generate a permanent plate mesh at this location using the merge mesh option. Note that this is an irreversible process and should be used after all modification. If we go back to the geometry page, see, a plate mesh is generated at this location with triangular plate element. Check this mesh. This is one of my density line. This is another one. All plates are divided along these lines. This is the region that we have declared, and we can easily select these plates. Also, all the internal members are properly divided to eliminate any beam plate connectivity issue. We can further revisit the parametric model page, and if required, remove this mesh and regenerate again with modified inputs. Like we can generate a fine mesh or add a new density line. This mesh generator has the flexibility for future modification, and that's why I think it is the best option to generate a plate mesh. Using this parametric model, we can generate a plate mesh for the entire slab. This time, I am going to select the nodes where the orientation of the slab change. We can easily skip the internal nodes where the boundary is in a line and select those nodes where the direction change, like the balcony or the cutout portion. Once done, we can select the type as slab, fix a target element size, add few openings if required, and this is the final mesh that is generated for the entire panel. See how the mesh is generated properly, maintaining all the connectivity at internal levels. This is how we can easily generate the plate mesh using advanced mesher. In next part, I am going to add a shear core at this location and discuss how we can design a wall using advanced concrete design module. Stay tuned and keep watching.